Hi everyone. Thank you for coming. We will start in around 9 minutes, so we still have some time. Thanks for your patience. In the meantime, you can check out our guest speakers' website, and I posted in the chat some relevant papers related to the talk today. So feel free to check them out in the meantime, and thanks for coming. Hi everyone, we'll start on top of the hour, so we'll start in around 4 minutes. Thank you for coming. And yeah, in the meantime, please check out the website and the papers that I shared in the chat. Will be a really interesting talk. Thanks for coming. Hi, Serena. How are you?
Hello, how are you?
Good, good. Hearing. Hi, Mayor. How are
Oh my
you?
God, what a title. What a title. First solid state light driven nanomotor. Like, I mean, come on. Like, everybody on Clubhouse should be up in here, dude. That is freaking interesting. You know what I'm
Gonna,
saying?
gonna be cool.
How are you, Katerina? How are you, Serena?
Good, good, good. How are you?
Good.
We're good.
Awesome.
Hi, Frank. How are you?
I shut down. I
Oh,
shut.
hi.
I shut down the room to bring. I told everybody I'm coming. When they kept going, I told everybody I'm gonna go over here to this other room. And, like, I had a room going. I was like, yeah, I'm definitely going in this room. You know. Uh, so we should have more people kind of following in, probably from the other room I was just hosting. We had like 30 people in there. I think a lot of those are gonna come in as they wind that down. But I'm super excited about this.
Yeah, me too. I'm also really excited. Wait, Sorry, I'm really bad at making people moderators. Go ahead. Thank you. In the beginning, I like share on Facebook and stuff. I don't even use Facebook anymore except for sharing the stuff. Actually, I don't know. Does anyone still use that?
There as well.
Yeah, come on, everybody, hit that share button and put something cool. Get people in here. This room needs to grow.
So yeah, our guest speaker should be here. He sent me the slides already a few days ago, and I sent the link again just in case, because of the time difference. I feel like sometimes people get mixed up. We had that a few times, so just in case, I usually share the link again a few minutes before. So, anyways,
Yeah, I just shared it.
Oh, he's out of Berkeley. Huh. Okay.
how was everyone's weekend? Happy Monday.
Well, I was up kind of late last night. No, it was okay.
Yeah, yeah. Serena had a really cool little social room. We were talking last night. That was fun. That was interesting.
It was a little impromptu room. It kind of went on for a while, but
Does somebody
yeah.
see our guest speaker? Says is in the room, but I don't see him.
Oh, I hope he's in the right room.
that's a good. That's a good point. Um, I see we got Dimitri, Early, Chris, PV, and P. Press.
Yeah, wonder what room he's in.
Yeah, I just wrote him to just restart the app and use the link I just shared. Dimitri is our guest speaker on Thursday, and he will give a really cool talk about these ETA tools that you remember we talked a little bit about it last week with the other guest speaker.
Yeah.
Yeah, so he will share those ETA tools to measure blood pressure continuously. Dimitri, we had the guest speaker here, and he said how important it would be to have like continuous blood pressure measurements, especially at night, So we said, "Oh yeah, you're coming." So that's pretty cool. Thank you.
Yeah, Dimitri, if you want, come join us on stage if you can.
Yeah, we just had the introduction room like 2-3 hours ago. Hi, Dimitri. How are you? Welcome, welcome again. I haven't
Hey,
spoken
how are
with
you?
you forever.
Yeah, just wanted to learn how this whole thing is going on here and to prepare for the Thursday talk.
Hi, Dimitri.
And this one seems to be
Hi, everyone. Couldn't speak very much. Sorry. Hi,
Hello?
Jingang.
Hello? Can you hear
Yes,
me?
Hello.
now we can
Glad you
hear
made
and
it.
see you.
Yeah, I think,
Yay!
I tried to join with my desktop, but doesn't work, so I have to log in with my phone.
I'm glad that yes, I don't know the club deck. Was it the first time you logged in with desktop? Sometimes the first time it's kind of buggy. It helps like just restarting the apps, and then usually the second time it should work. Sometimes the unmute button doesn't work, and people that speak the first time in the room. I
Yeah, I
don't.
just couldn't find the unmute button, so. Okay, anyway, thanks for waiting. I'm finally here.
Yeah, you're here. We can. Yeah, we can start slowly. Let me just share that you're here on on Twitter. And because if you share on Twitter too early, then your name wouldn't have been mentioned. Like if you're not in the room and I share it on Twitter before you're here,
Mhm.
then nobody knows you're actually here. Sorry about that. Okay. So welcome everyone to the Science Society, and of course a special welcome to our guest speaker here, Dr. Jingang Li. And before we start, let me introduce you to the audience a little bit so they get to know you. So Dr. Jingang Li, he's a postdoc working in the field of optics and photonics. And he is currently at the University of California, Berkeley, and he received his PhD in materials science and engineering from the University of Texas, Austin, in 2021. And he did his bachelor in science in applied physics from University of Science and Technology of China. His research focuses on exploring fundamental and applied optics, including photonic materials, optical manipulation, light-matter interactions, and optical measurements for broad applications in electronic and photonic devices, optoelectronics, microrobotics, additive manufacturing, smart materials, cell biology, biosensing, and disease diagnosis to solve challenges in human health, information technology, energy, and environmental sciences. He has already, as a young scientist, published 15 first authorship papers in really great journals like Nature, Communication, Science Advances, Chemical Reviews, and so on. And he has been highlighted by a lot of science media outlets and recognized a number of prestigious awards, including Material Research Society Graduate Student Award, UT Austin, and so you can find more about his research, as I said before, in the website that I posted on top, and I will shortly switch that link after our short interview to the presentation. And I also shared papers that are relevant to this talk today in the chat, so people can check them out. So welcome. And before we go ahead and start with your presentation, Serena will ask you a few questions, a few interview questions. That's okay with you.
Yeah, sure.
Well, hello and
For
welcome.
the detailed introduction.
Oh, okay. So, just for the benefit of the audience, we like to get to know a little bit about more about you and how and what drives you and how you got here. For our first question, can you think back at a time where was there a defining moment where you knew early in life that you wanted to get into science?
Yeah, so I say it started really early, maybe when I was a kid. So if you can think about, I'm not sure if you guys have played the game like called marble game. That is, you use some very small glass ball and then use your hand you to manipulate those marble balls, and you just shoot one glass ball to hit another ball, and kind of like I was really good at playing that kind of marble game when I was a kid. And later on, when I learned in middle school, high school, and then I learned like how, actually that like marble game is kind of is all driven by physics. You have to give the ball a momentum, and then it's hit another ball, and then there comes to the momentum transfer and exchange. So I will say I kind of get interested in those physics when I was playing like different games, including the marble game and other games when I was a kid. And then back into my middle school and high school, I was I was also curious when I learned learn physics to explain those phenomena in my daily life, and then I became really interested and I wanted to explore more physics and explain more things that I can see in my daily life. I think that all comes from and I think that all of that things leads to my like undergraduate and also graduate studies to like make me um, like work hard to learn more things and try to discover new phenomena and explain things.
It's fascinating to go from embracing Newtonian physics through marbles to the quantum regime that you're talking to us today about. Could you take us from that point to the work you're going to share with us today?
Yeah, actually, the work I'm going to share is also very close related to that marble game. I'm going to talk about the optical manipulation. So instead of using our hand to manipulate those big stuff, here I'm talking about big is, compared to the particles I'm going to talk about in my presentation later. So like for the marble game, what we're talking about is like a glass ball with a diameter of like 1 to 2 centimeters. But for the nanoparticles, it's gonna be the size of several hundred nanometers or micrometers, and that is kind of like several orders of magnitude smaller than the marble game I'm talking about. But the basic principle is similar. So in marble game, we are using our hand to manipulate and control the motion of those glass balls. And here, for optical manipulation, instead of using our hand, we are using a light. We explore the light and light matter interactions, that is the interaction between light and those nanoparticles, and to control the motion of nanoparticles. I will say that that's actually very similar stuff what we are working on. Actually, a lot of research work are kind of like a lot of research work are an analogy of those marble game we played when I was when we were in childhood.
Wow, that's fascinating. Well, okay. So Katarina's just pinned the link to your talk above, so the audience can follow along.
Mm-hmm.
And with that, I'll hand you the mic, and I'll look forward to your talk.
Okay, yeah. Okay, welcome everyone, and thanks for the invitation and introduction. I'm here very honored to be here to present my recent research. Um, the title of this presentation is First Solid-State Net-Driven Nanomodels. That is one of my recent research work. But to begin with, I would like to share the complete story of my doctoral research. Here, if you look at the page 1 of the slides, that is a revolution in optical tweezers, non-invasive manipulation, and solid-state net-driven nanomotors. So uh, the the major part of my PhD research is I try to the new optical manipulation techniques to solve the current limitations in optical tweezers. I will introduce you optical tweezers later if you are not familiar with that. And then I will introduce like 2 directions I'm working on. Um, yeah, as Katarina introduced, I'm currently a postdoc at UC Berkeley, and if you go to slides 2, the research work I'm going to present here is all based on my PhD work at UT Austin. There are some key references as posted in the message, and also before I get into my work, I would like to give acknowledgements to my supervisor, Professor Yuebin Zheng, for his guidance and support, and also a number of collaborators from UT Austin and other institutes, and also the collaborations from my previous group members, and also all the funding agencies to support our work. Okay, then if we go to slide 3, it will be an outline of this of today's presentation. So this presentation is actually the same one I presented in a recent conference. So I understand that there are people from different fields, and actually I'm not sure how the clubhouse will work. But if you guys have any questions, just feel free to stop and ask. We can stop anytime and answer your questions. And yeah, so I will also try to be using some plain language to explain everything. But if you feel hard to understand, just stop anytime. So I will first give an introduction about optical tweezers and what it is, and why it is interested to working on those optical tweezers, and what are their limitations. So that is like how we want to improve them. And the second, well, I will introduce my PhD work in 2 directions. The first direction is to develop non-invasive opto-refrigerative tweezers to achieve the safe manipulation of different kinds of biological objects and nanoparticles. And the second, I will talk about the solid-state optical manipulation, that is to manipulate those nanomaterials on the solid substrate directly. And finally, I will give a conclusion and some take-home messages. So first, a bit introduction. If you go to the slide 5, this slide is basically where I'm here to introduce very briefly about optical tweezers. So if you see the name optical tweezers, that is similar to the tweezers we use in our daily life, but it uses light to capture small objects. So how it do is, if you see the imaging, so when we focus a light beam, that is usually a laser beam we are talking about. So if you focus a laser beam tightly, it will has a focal plane that is a very bright spot, small focus spot, and in that spot, the light intensity is strongest compared to other place. And this light intensity gradient will have an optical gradient force that's generated because of the momentum transfer when light hit the particle. And this optical gradient force will lead to a total force that trap the nanoparticles to the center of the laser beam, that is to the strongest light intensity place. And this technique called optical tweezers is invented in like 50 years ago, and it has been awarded 2 Nobel Prizes in physics. The first one is a Nobel Prize in 1997 by Stephen Chu and co-workers for their research in laser cooling and trap of atoms. And lately, very recently, it was awarded another Nobel Prize in physics in 2018 because you can think about if we can use those optical tweezers to trap nanoparticles, we can also trap biological cells and molecules and a lot of other stuff. And this this needs their in applications in biological systems has made them another Nobel Prize in 2018. So briefly speaking, for summarize those optical tweezers, they are like using light, laser light, to capture and manipulate different kinds of objects, including nanoparticles, biological cells, molecules, a lot of stuff you can think about, very small stuff. And they can be used for a lot of applications to, to measure nanoscale interactions, to study biological process and a lot of things. It is a very powerful technique and has a lot of advantages, including using light to remotely control materials and to manipulate different objects with different sizes ranging from nanometer scale to micrometer scale, and it can be integrated with computer to achieve programmable control. However, despite of those advantages and 2 Nobel Prizes recognition, actually optical tweezers um, are not not best so far. They still have some limitations, and the first limitation, and the main limitation actually is caused by its principle. As you can see from the picture, it requires the laser beam to be very tightly focused to one spot to generate enough gradient force to trap the particles. So it requires complex optics that, some lenses and objective with with good numerical aperture to generate those focused laser beam. And the second is if it relies on the gradient force, so you have to have the optical contrast between the particle and the environment. And because of those limitations, it usually requires very high optical power to trap biological cells or very small nanoparticles. And this high optical power can cause damage to those nanoparticles. So briefly speaking, it is not safe, and it is not that general to all objects, because you need to have those high optical contrast between the objects you are manipulating and the environment. So in order to overcome those limitations, if you go to slide 6, you will see some previous efforts to address the high power issue. So researchers has proposed different techniques to achieve optical trapping and new optical tweezers using very low optical power. For example, in the left panel, it showed the plasmodic tweezers. It used very tiny metallic nanostructures with very strong enhancement of electric field to generate optical gradient force with very low optical power. But you can this technique can trap nanoparticles with low power, but you can see from the scheme, it can only trap the object at the two end of the plasmonic antenna. That is, you can only trap those particles at the hot spot. And this hot spot is fixed as when you fabricate those nanostructures. So that kind of manipulation is not dynamic. You can only trap it, but you cannot move after the trapping. And the second, the middle panel and the right panel shows some indirect method that explore the indirect optomechanic coupling that is a light-controlled electric or temperature field. Here is like, for example, the optoelectronic tweezers in the middle panel use light to irradiate a photosensitive substrate to generate a non-uniform electric field, and then to explore the particle migration under the non-uniform electric field to trap those objects at the light illumination region. And the red panel shows a similar thing, that is using light to irradiate optothermal substrate to generate a non-uniform temperature field. And those nanoparticles then will migrate along the temperature gradient to be trapped at the laser center. So all of those techniques can overcome the high power issue to achieve the trapping of nanoparticles with relatively low power, that is as small as 2 or 3 orders of magnitude lower than optical tweezers. However, if you go to slide 7, you will see even though this techniques has achieved no optical power trapping, but still there are 2 major limitations. The first limitation is optical heating. If you recall the last slides, so there are like different kinds of techniques to achieve low power optical trapping, but based on our common sense, whenever light hits something, it usually heat it up. So especially for the plasmonic tweezers and optothermal tweezers, those high electric field enhancement and high optothermal conversion actually will amplify the optical heating issue. And this optical heating will cause thermal damages to nanoparticles and especially some cells and molecules, for example, protein and DNA. Those biomolecules, if you trap them and but heat them, then it will be, kind of like those biomolecules will degrade and make no use for the future studies. So this optical heating is actually a very great issue in the optical manipulation field. And the second issue is is all of those techniques actually they are manipulated in liquid environments. So if you're going to use the nanoparticles you are manipulate for some applications in on-chip devices, it will be very difficult because you have to remove the liquid, and this will cause the undesired pattern collapse due to the capillary force. And meanwhile, because particles are manipulated in liquid environment, so if you want to achieve precise assembly of nanomaterials, it will be challenging because of the strong Brownian motion when it comes to a nanoscale. So Brownian motion means that when you have particles, very small objects in liquid environment, it will move around very randomly. And this Brownian motion is stronger when the size is smaller. So when you go to nanoscale manipulation, those Brownian motion is very strong, and you need very large force to overcome the Brownian motion to achieve precise manipulation. That is another challenging for the manipulation field. So then it comes to my motivation of my doctoral research. So my motivation is to overcome these 2 limitations that are not solved by the previous efforts in developing new optical tweezing techniques. The first one is to avoid optothermal damages, and the second one is to achieve the manipulation of nanomaterials directly on solid substrates to avoid Brownian motion and capillary force. So that's all about the introduction part, and then I will go to the first direction I'm working on, that is the starting page, slides 9. Are there any questions so far, or I can continue? Okay, so I guess I just continue starting slide 9. So
A quick question regarding
yes,
slides number 6, the middle one, the what do you call the
optoelectronic tweezers, yes.
Right. So is this another route, alternative, or is actually your work is building on this schema?
So yeah, this the both the optoelectronic tweezers and optothermal tweezers, they are both extensions of previous optical tweezers, but they are based on different mechanisms. The first, the optoelectronic tweezers is to explore the particle migration on the electric field, and the third is based on particle migration under a temperature field. They are not. They are not actually. They are new extensions, but later you will see my research work is completely different from those two. Yeah, they are all based on different mechanisms.
I see. Thank you.
Okay. Now let's go to the slide 9, and I will introduce my first work. I termed it opto-refrigerative tweezers. So as we mentioned before, in nature, actually, when you have a light like solar light or laser light, when you use the light to heat something, usually it will heat the materials up. But this, as I said before, is actually not designed for the optical manipulation, especially for some biological objects. So what about we to use like optical cooling? Actually, yeah, it is possible. It sounds may sound like very weird, but there are actually something called laser cooling and has been developed before. So what we do is we have those special material. If you see the substrate, it's like ytterbium doped YLF substrate. So it's kind of like a special materials that we synthesized. And this material, the cool thing is that when you use a certain wavelength laser, that is 10-20 nanometer laser, when you use this laser to heat the material, it actually cools the materials. And this cooling will cause, will generate a will generate a temperature gradient that is colder at the center of laser beam. And this laser cooling is because you have these ytterbium ions, that is YP ions, shows in the middle panel of slide 9. And if you use the 10-20 nanometer laser to pop, to excite the ion, and this material will absorb the photon and later will emit another photon with a higher energy. And this will cause the total energy loss in the material, and so will cause the cooling of the materials. And in the red panel, which shows that when we excite the material with 10-20 nanometer, and you can see we can observe the photoluminescence, that is the emission of new photons at a shorter wavelength. The emission at shorter wavelengths means it's means the emission of photons with higher energy. That further confirms the optical the laser cooling laser cooling theory. And the general concept of our opto-refrigerative tweezers is to use laser cooling to cool the substrate to generate a cold spot, and then to explore something called thermophoresis to trap the objects to the cold region, that is the laser center. The thermophoresis means describes a phenomenon in nature that most objects, including colloidal particles, molecules, and cells, they will tend to move from the hot to the cold under temperature gradients. Because in nature, most of things they are like thermophobic. They do not like heat, and they want to be something cool, something they want to be somewhere cold. So based on the laser cooling and thermophoresis, we can trap those objects to the cold region at the laser beam center. That is the general concept of this of the opto refrigerative tweezers. And then if we go to slide 10, here we show the analysis of laser cooling and the thermophoretic force to achieve the optical trapping. So the left panel is temperature mapping we measured experimentally using a thermal camera. And you can see the center temperature of the center is more than 10 degree cooler than the environment. And we derive the temperature gradient mapping from the left panel as shown in the middle panel. And you can see there are very strong temperature gradient as high as 1 to 10, 10 to 7 degree per meter. And under this very strong temperature gradient, we calculated the force and the trapping force and the trapping potential for typical colloidal nanoparticles as shown in the red panel. And the result shows that we can achieve very stable trapping with large enough forces to trap colloidal nanoparticles at the center of the laser beam. And slide 11 shows the results of the trapping and the manipulation of single nanoparticles. So there is a video there. I think if you download the slide, you can play the video, and it shows the trapping of a single fluorescence nanoparticle, and when the laser is turned on, and when we turn off the laser, the particle will be later released. And in the later half part of the video, we show that when we trap the nanoparticle, we can further move it to somewhere else on demand. That is the dynamic manipulation of those nanoparticles. So for the trapping, we achieve very high trapping stability, that is similar to plasmonic tweezers and optical tweezers. But here we use one order lower optical power. The reason is because we rely on the thermophoresis to trap the nanoparticle. So in principle, we do not need the strongly focused laser beam. So we can use much weaker optical intensity to do the work. And later, if we go to slide 12, that shows the non-invasive trapping of nanoparticles and biological molecules based on our technique. So in the upper panel, we show the comparison of this technique with traditional optical tweezers. As you can see, for the optical tweezers, so if you see the panel B, for the optical tweezers, there is a fluorescence quenching when we trap the particle for 1 minute, and the fluorescence intensity dropped for more than 35%. But for our opto-refrigerative tweezers, the intensity remains for more than 90%. And this non-emissive trapping shown by the enhanced stability is because of two reasons. The first reason, as we mentioned before, is we do not require the highly focused laser beam to achieve the trapping. So we can use a weakly focused laser beam with lower optical intensity. In that way, we reduce the photo-induced damages. And the second, of course, is because we have laser cooling. So the particle is trapped and maintained at a lower temperature instead of, for optical tweezers, there are some heating effect. So this will completely avoid thermal damages. So we can achieve much better stability compared to the optical tweezer. Panel C and D, we show in addition to the nanoparticles, we can also trap and concentrate protein molecules and other biomolecules without molecules because we can keep them at low temperature. So this capability will be very interesting and promising for those biological, biological and biomedical engineering fields, that we can trap those thermosensitive biomolecules and simultaneous cool down temperature and to study their interactions with other biological objects such as cells, cancer cells, or viruses, and for a lot of things in drug development and disease diagnosis. Yeah, so this is the first part of my doctoral research to develop opto-refrigerative tweezers. And next, I will go to the second direction, talking about the optical modulation on solid substrate. Before that, are there any questions about the first part?
Sure. I'm curious about how much of a range or range control on the thermal gradients that you're able to control. I see the temperature range you showed on the plot down to 285 or so. So you get 10 degrees. Do you have other ranges or gradients that you? I mean, how much control do you have over those parameters?
Yeah, that is a good question. So this laser cooling and temperature gradient can be controlled. You can think about in several ways. The first way is to control the optical power. So if you okay, I don't think I have that figure, but if you look at the figure in that paper, so we can control the optical power to achieve different cooling degree. So the temperature will drop more when you increase the optical power. So that is actually very straightforward, right? And the second thing is we can control the laser beam diameter, and that will cause different temperature gradient because the temperature gradient is dependent on both the temperature drop and also the spatial resolution of temperature distribution. So if you increase the laser diameter, the effect will be actually the temperature gradient will be weaker. And the third way you can do is to tune the, if you go back to slide 9, you will see the substrate is ytterbium ion doped substrate. So you can also tune the doping concentration of those ytterbium ions to achieve different cooling capability.
Thank you.
Dr. Lee, maybe relevant to this question, and it's a bit of a selfish question because I'm working at the warehouse and I can barely pay attention, but I will watch the replay. Maybe at some point, if you can quickly describe some, maybe like normalized statistics about the efficiency of this motor, nanomotor light driven, like in this, maybe I don't know if the vocabulary could be like gain in electrical engineering related to power output, but just some sort of measures on efficiency of the motor and if there's a loss or a gain of efficiency based on the standard set by the optics or a light driven medium. If there's any normalized statistics or some vocabulary you could provide, that'd be really helpful to me. And I'm sorry I can barely pay attention at this time, but I will watch the replay and pay close attention. And I appreciate your presentation. Thank you so much. Thank you so much.
Okay, yeah, thanks for the question. But I will go to the last part. So I will go that when I talk about the nanomodels, but now we're not
No problem.
not there yet.
Thank you.
Yeah. So and if you read my SS nano paper, that I believe the link is there. So actually we have a supporting note in the supporting information, and also in the main text we kind of mentioned that how to calculate the efficiency you are asking about. So we do have a way to calculate the efficiency of like to convert light into mechanical energy. Yeah, we do have that.
I shall pay attention. Thank you for the reference and thank you for the presentation again, Dr. Lee. Thank you. Gracias.
Yes, please.
A quick question, Jingang. The so this so the target particles are suspended in some liquid on top of the ytterbium substrate.
Yes.
What kind of solution that you're using?
So yeah, that is a so
You're
far.
cutting out.
Mm-hmm. Yes. Okay, so for the laser cooling, so far as the first element to minimize the absorption of the environment solvent. So we are using heavy water for the trapping experiments in this experiment, but in principle, we also demonstrated the laser cooling of those stuff in water or PBS like biological media. So I will say heavy water works best, but some like water or fit in other like biological media will also work. Yeah, but in the experiments for the nanoparticles, we are using heavy water because we want to minimize the absorption at the 10-20 nanometer. Because in heavy water we'll have like 1 order less absorption than normal water. Yeah, that's a good question.
Thank you.
Any other questions for this part?
No, I think we're okay. Thank you.
Okay.
Sorry, is it just me that
Yeah.
you sound at some point you're cut out, or maybe it's my signal, or is it how's others? Did you hear similar effect?
Not right now. Maybe very short in between, but right now it sounds fine.
Good, thank you.
Yeah, I apologize if the network here is not that good. Yeah, probably it's because my signal here is not that good. Yeah.
Right now
If
you're
it
fine.
okay,
Good.
just let me know if there's something unclear so I can repeat. Yeah. So now if we go to slide 14, in this slide, going to talk about another direction, that is to explore and develop new manipulation techniques to achieve the optical control of nanomaterials directly on solid substrate. So before I go into that, so I will let's imagine if we do it in our real world. So imagine we have a box sitting on the ground and you want to push the box, so you overcome the friction force between the box and the ground. And if the box is heavy or if the surface is very rough, you will have to push it really hard. And if we put the box in order, however, now you can think about, you can push the box really smoothly without pushing very hard, right? So that case actually is the same when you go to the small nanoscale world. So far, why people want only like work on the optical manipulation of those nanoparticles in fluidic environment? That is because if you put nanoparticles on the solid substrate, if you want to push the nanoparticles or you want to move them, the friction force is very strong. We all know that a gecko can stand on the wall and they can like walk on the wall because the van der Waals force is very strong, can bend their feet with the wall, right? And then when you go to nanoscale, when you have a nanoparticle sitting on the solid substrate, the van der Waals force is very strong to bend the nanoparticle. And if you want to move them, actually you have to have a very large force. And this force is usually not achievable using light. So you have to use something mechanically to push it very hard to move the nanoparticle. That is the reason that people previously cannot achieve the manipulation of nanoparticles on solid state. So okay, now we understand the challenge here because of the van der Waals friction force. So in slide 14, I show that we come up a new way to overcome this challenge by something called interfacial engineering. That is, we introduce a interlayer between the nano substrate to substrate interactions. So here we take the a surfactant called cetotrimethylammonium ammonium chloride, that is CTAC, as an example. So, but in principle, you can use materials as long as properties. So if we introduce those CTAC layer in between as a as an interlayer, and what happens is at room temperature, when the laser is off, this layer will be in solid form, and the particle will be just sitting as substrate and bounded by the van der Waals force. But if we have laser on, for example, for gold nanoparticles, the optical heating of gold nanoparticles will cause a local temperature rise, and this temperature increase will cause a phase transition of this CTAC layer, as shown in the bottom in the upright panel. When you have this phase transition, the CTAC will change from a crystalline solid phase into a quasi-liquid phase. And now the things happen just like we move the box from the ground to the water. And in this case, the friction force is reduced significantly. So meanwhile, we can use optical force to move the nanoparticles. And as shown in the bottom right panel, so what the thing happens is when you have the laser here, the optical heating will cause the phase transition. And meanwhile, when you do not worry about the friction force, and the optic force can be large enough to push the nanoparticles away. So if we go to slide 15, there will be one video showing the optical manipulation of different colloidal nanoparticles on solid substrate by this technique. So basically, if we move the laser, and we can push the nanoparticles to anywhere we want. And this is a contactless and non-invasive manipulation technique. And it can be widely applicable to different materials, different particle sizes, and different shapes. And we can monitor the manipulation process in situ, and we can also tune the optical wavelengths to achieve the best performance. And the good thing is, as we mentioned in the motivation page in the introduction, that there is no Brownian motion. And if you want to immobilize the nanoparticle, you just turn off the laser, and you will see from the video that there are actually some particles just sitting around still, right? Because if you do not have laser on it, they will just be like sitting in, and there will be just be like particles in steel. If you want to move them, just shine the laser on and push them to anywhere you want. And another thing I want to mention here, CTAC, the interlayer between the particle and the substrate, the phase transition is reversible. There is no materials damage, and you can achieve the manipulation through the same route, like very in a repeated way for many times. So far the manipulation of different colloid particles, and in that way we kind of extend the manipulation, the working environment of optical tweezers from fluidic environment to the solid substrate. And in the next slide, slide number 6, because we are working on those manipulation of solid substrate directly, so we can achieve the dynamic patterning of the same nanoparticles and nanomaterials into different patterns, so in a sequence way. So like for example, there are 4 gold nanoparticles, and we pattern it into a L-shaped pattern, then into a square, and then to a mirror L-shaped pattern, and then to a straight line. So that put the 2 silicon nanoparticle and 1 gold nanowire into a Y letter, and then reconfigure it into the Z letter. And in the next slide, slide 17, we show that because there is no Brownian motion, so we can just move the nanoparticles to anywhere we want. Like that, this is very good the manipulation in liquid environments. Like for them, when you move the nanoparticle, you trap them, there are still very strong Brownian motion that they are moving around. But here, when you turn off the laser, the particle just sits. So you can move it to anywhere you want, because you need to judge like where the particle, whether the particle is in the right position or not, and where, like, when to stop. So if you have some very advanced imaging software that can help you to define the right location, you can potentially achieve like the resolution at a really nanoscale. So here, like, by our naked eyes, we demonstrate the precise alignment of 1D line shaped, and also 2D arrays with silicon nanoparticles with a position error of less than 100 nanometer and 200 nanometer for the both cases respectively. And of course, this is not the end. We can definitely improve this position error by using like advanced imaging techniques. And last, if we go to 18, this manipulation platform is further integrated with an optical spectroscopy that allows us to not only real-time checking the manipulation process, but also we will be able to measure the optical scattering property of the nanostructure we are working on. As a very simple demonstration, so you can see in the upper panel, when you move the two gonal particles together, it will become a dimer when they are close enough. And we can also check the scanning electron microscopic imaging, and we will see they are indeed like almost other. So if we check the we'll see from a demo, we will see the peak of gonal particle. They are like split into two, consistent with our simulation. So far, like with the integration and the capability to dynamic manipulate those colloidal nanoparticles on solid substrate, and with nanoscale resolution, develop this solid state optical manipulation as a promising platform.
Now you're breaking up. Is it maybe sometimes it's helpful to turn off the Wi-Fi and use cellular data if you're on your phone?
Okay, is now okay?
Yeah, now we can hear you again.
Okay. I think the Wi-Fi is the issue. I'll use cellular data instead. So I'll repeat the conclusion in this page. So with the in situ optical spectroscopy and the capability to manipulate those nanoparticles and assemble it into different pattern in a reconfigurable way with nanoscale accuracy. So we are developing a really powerful platform for the material scientist and optical physicist to assemble nanoparticles into different structures, and we can also very precisely tune their position, and also to study their coupling and interactions. And this will also allow us to further to design like new devices to achieve different functions as nanoscale like solid state devices. Yeah, that is the first part of the solid state manipulation work. Are there any questions about this part?
So far, Frank, everyone is okay? I think we are good. Thank you so much for asking.
Okay, thank you.
Again, just quickly regarding the, so it's a little bit counterintuitive for me that I can understand there's a thermal force that when you're immersed in liquid, but now you're without liquid on a solid surface. Where those thermal gradient force comes from.
Okay, yeah. Sorry, I didn't explain very clearly. So if we go back to slide 14, um, the the force actually there is not based on the thermal gradient. So you can think about like the upper part of the, like the particle is surrounded by air, right? And there is no liquid based like phoretic force. So the particle is moved by optical scattering force. Yeah, sorry, I should mention that. So yeah, and I should also mention the name of the technique. So you see that we term this technique optothermally gated photon energy. So the optothermally gated is because we have a CTS layer. They are kind of like an optothermal gate. When you have the laser on, when you have the optothermal effect, the gate is open and the particle can be moved. So we call this CTSA an optothermal gate. And the photon energy is because the manipulation is based on the scattering force. That is kind of you are using light to push the nanoparticle. So using a photon to push the nanoparticle based on the scattering force. So we term this technique optothermally gated photon energy. Yeah.
I see. That's a very different physics. Okay, I see. Thanks for explaining. Please continue. Thank you.
Okay. So later, if we go to slide 19, so later there are two works. Is like we extend the solid state optical manipulation into reconfigurable assembly and finally the nanomotors. So they are all based on the previous nature communication work. That is, they share the same concept, to use the optothermal gate (CTAC) to modify the particle and substrate interactions. So in the slide 19, we showed as we just mentioned in slide 18, that we showed that those new technique can serve as a powerful platform to study to assemble reconfigurable nanostructures and to study their interactions. So in this work, we showed one typical example that is so-called reconfigurable chiral structures. So probably I should also spend some time explain what is chiral. So chiral structure is like is for describes the structure that cannot be overlapped with their mirror imaging. They are very common and universal in our daily life. For example, our hand is chiral. That is why like sometimes the chiral structure is also be called left-handed structure or right-handed structure, and also in chemistry and biology, a lot of chemicals and biological molecules, they are all chiral, including sugars, DNA, and also a lot of drug molecules. They are all chiral. So for these chiral molecules, there are like two structures of these molecules. Like one left-handed structure and the other is right-handed structure. They are mirror images of each other, and they, despite they are composed of the same component, same items, but their chirality will determine their physical and chemical structures. So this will lead to very important studies in biological and biomedical engineering. And so people are developing a lot of chiral nanostructures, trying to exploit the enhanced light matter interactions to detect different chiral molecules and to sense those molecules to for safe drugs and bio and disease diagnosis. So here, what we do is we use the optothermally gated photon energy technique to construct a chiral nanostructure with a silicon nanoparticle and a silicon nanowell. So if you see the up left panel, so what we do is we manipulate a silicon nanoparticle by using laser to push it to the to somewhere close to the silicon nanowell. And the right side of the slide has a video showing how we do that basically it's just very similar to what I showed before. It's basically just like move the nanoparticle, and you can manipulate and move it, push it to the like near the silicon nanowire, and based on the relative position of the silicon nanoparticle to the silicon nanowire, we can define the nanostructure to be left-handed structure, that is LH, and the right-handed structure RH, showing in the skin optical imaging and also the scanning electron microscopy images. So that is the how we construct and those chiral structure. And in the next slide 20, we show that because we can manipulate those nanoparticles on solid substrate, so we can achieve the dynamic control and reconfigurable assembly of those nanoparticles. For example, there are like four columns in the slide. So if you see the left column, which shows a skin and optical imaging of the nanoparticle components before the assembly, and the second column, we're showing that by pushing the silicon nanoparticle to the left end of the nanowire, we can assemble these two into a left-handed structure. And then in the third column, by moving the silicon nanoparticle along the silicon nanowire from the left end to the middle, we are transforming the left-handed structure into an A-chiral structure. That is, for A-chiral structure, they are like symmetric. There are no chirality. And finally, in the last column, we move the silicon nanoparticle from the middle into the right end, and then we transfer it into the opposite-handed structure. That is a right-handed structure. So in the bottom panels, we showed the using our in situ optical spectroscopy to measure the optical scattering at different circularly polarized light. So for the left-handed structure and the right-handed structure, you will see it shows you can see very distinct optical spectra under the different kinds of different circularly polarized light. But for the A-chiral structure, it shows almost the same spectra under the circularly polarized light. That is because they are A-chiral, so they are not responsive to those chiral lights. If we calculated the difference of the optical scattering under the left circularly polarized light and the right-handed circularly polarized light, and we calculate the circular differential scattering spectra as showed in the bottom left panel. So you will see for left-handed and right-handed structure, the optical spectra actually showed a handiness flipped feature, and that further confirms, we can tune the position of the signal particle, and we can assemble, we can tune dynamically control the property of the structure we are assembling. And further, we can tune the function of this nanostructure for different purposes. That is like we demonstrated to use this opto-thermocapillary photoenergy to assemble active devices. Like for example, in this specific case, we can control the silicon nanoparticle position to control the light scattering. We can selectively let the structure to scatter more left-handed circular polarized light or to scatter more right-handed circular polarized light. And this is very important for some applications, in chiral light source and also in optical communications, and because you can use those handiness of light for quantum communications and even quantum computing. And finally, for this work, in slide 21, we showed instead of like we can tune the chirality of the structure, we can further use this structure to sense and detect the biomolecules. That is also the initial motivation of developing those chiral structures. So we show that when we have the left-hand and right-hand structure, and we take the molecule called phenolalanine, there are two left-handed and right-handed phenolphthalein molecules, and they are very important in drug in drug in drug development, because one enantiomer is a safe drug, but the other is toxic. So it is very important for we to distinguish the different chirality and to detect the purity of the phenolphthalein molecules. So you see from the middle figure, that we can based on the data lambda, that is um, we measure the peak shifting after the adsorption of the molecules in the left-handed and right-handed structure. And we calculate the difference between the left-handed structure and the right-handed structure, so we can get opposite result for the left-handed and right-handed molecules. And so we can achieve the very sensitive and label-free detection of this chirality of these chiral molecules, and this is very promising for the to detect biomolecules for disease diagnosis and for biomedical engineering. Yeah, that is the work. We use opto-thermocapillary photoenergy to develop the tunable chiral structures for active light source, quantum communication, and also for the enhanced chiral sensing. Are there any questions for this work? So if not, we're going to the last work, that is Opto-thermocapillary nanomotors. That is also the title of the presentation. It's like the first solid-state optical nanomotors we developed. Yeah, but this work is also based on the previous nature communication work that we use CTAC layer. So if you see the slide 22, the up left panel, so we have a layer sitting between the silicon, between the gold nanoparticle and the glass substrate, and when we shine the laser on, there will be a phase transition of the CTS layer, and at certain we can tune the light wavelengths and some other conditions, then we can achieve the nanoparticle to to we can demonstrate the nanoparticle moving around the laser beam in a circular orbit way. So if you play the video showing the bottom of the slide, so you can see the nanoparticle is previously sitting on the solid subject, and then when you have the laser on, it will start rotate along the laser beam. So in this video and all the experiments, there is no water. So we are moving those small nanoparticles directly on solid substrate, because we're using the CTS layer to modify the particle substrate interactions. And the right side shows the the tracking trajectory of the nanoparticle. So you will see the nanoparticle, like for the in this 1 minute video, you will see the nanoparticle. They are moving around the laser beam in an almost perfect spread circle. So this is like the first demonstration of the light-driven solid-state nanomotor. That is a very small. The nanoparticle is 80 nanometer, and there is no Brownian motion. So you can see from the video that when we turn off the laser, the particle will just stay there, and if you turn on the laser, they can rotate again. So if we go to slide 23, in this page, I actually show some the mechanism and why this nanomotor can work. So this is because the gold nanoparticle has a symmetric shape. So you see from the left imaging that the nanoparticle is not strictly spherical, and because of this non-spherical shape, when the laser is on, it will cause the non-uniform temperature distribution at the particle surface. And because of this non-uniform temperature surface, there will be non-zero thermocapillary stress acting on the particle when the laser is on, and this thermocapillary force will later drive the nanoparticle to move around the laser beam. So this is different from the nature communication work. In the brief summary, is we are using those non-spherical nanoparticles, and we explore the coupling of optical force and thermocapillary force to achieve the stable rotation of those kind of nanoparticles. And we further demonstrate the experiment. We further demonstrate the modeling of those optical nanomotors. So if we see the slide 24, the left one shows a video of our experimental demonstration of nanomotors, and you will see there are many particles sitting around without move. That further confirms that we are doing it in the solid state. There is no water, and the middle and right videos, both videos shows the modeling process. That is, we calculate all the forces and torques, and then just input everything into MATLAB, and then this MATLAB will, automatically repeat the optical orbital rotation of our optical motor. That is so this is like the very initial demonstration of the first net-driven nanomotors on solid state, and we are further working on to improve the performance of this model. So as I think as one audience mentioned before, like how we calculate the efficiency. So we did calculate the the light to mechanical energy conversion in this case, and this conversion efficiency is also very comparable to the most advanced optical micro models in the current research field, but still that value is still very small because we are dealing with randomly shaped nanoparticles. So in the future, we are trying to design we're trying to do rational design of the geometry of the nanoparticles in order to achieve the more efficient light to mechanical energy conversion. And also, we are also very interested in using this nanomotor to for many other applications. For example, we are interested in to making this nanomotor very controllable, and so it can be even used to sense the air quality, because this rotation will be highly dependent on the environment. And if there are many air dust, we can monitor the air quality by the rotation speed. And the second is you can imagine those net-driven nanomodels can be used for a lot of lab-on-chip devices. For example, in the future, you can just using light to develop the mini drones in nanoscale for some very measurements and other purposes. And also these nanomodels can be integrated with other devices as a nanoscale power source to convert light into mechanical energy to replace some batteries and other energy sources. Yeah, so that is what I want to talk about the optical nanomotors, and it is still in the initial stage, but we envision that the future potential is very huge, and yeah, we are working on the future work based on this model. And are there any questions about this one?
Yeah, first of all, thank you so much for this wonderful presentation and explaining this so well to us in such a structured way. It was really a wonderful, really great presentation. And for controlling the structure of these nanostructures, what is the approach? Because I recently read different, and we had a guest speaker here about using DNA to control, like for example, tiny gold particles in to change basically light. And then there was a paper that came out that with DNA they controlled microtubules. Is that something you're considering, or are you maybe using machine learning approach or so to control basically the shape in the future?
Yeah, thanks for the question. Yeah, what I'm talking about is the latter case. Yeah, we're trying to different. It is a little bit different from like those like using DNA stuff. So we're trying to use, if you go back to slide 23, so you see the left image. So here is the particles we are using about. So it's complete random. So they are asymmetric, but they are random. So what we are trying to using something like machine learning or something like using numerical simulation, and we are trying to use like nanoscale nanolithography to fabricate gold nanoparticles with specially designed geometry that can provide the best net to mechanical conversion efficiency. Yeah, that's what I'm talking about. And for those like DNA stuff, it is also interesting because I've also read some papers about like DNA, and they are like very interesting way to using DNA they can control because they can control the different binding between the DNA molecules, and they can use DNA to assemble nanoparticles into different structures. And this structure is also they can also it's also tunable if the DNA is exposed to some external stimuli. Yeah, I think that concept is actually similar to what I'm discussing today. So we are also trying to do the similar thing, but we do not rely on DNA. So we are relying on the light itself. So we use light itself to assemble different structure, and we use light to disassemble it, and then we use light to assemble it again. So we are doing it in compared to their DNA approach. I will say it will be uh, if you think about those working conditions, the experimental conditions is not as it's not as complex as there because we do not have this DNA stuff. And but so far we are still in the early stage, and we are because for DNA assembly it has been studied for decades. But now we are still in the initial stage, and we are trying to make those optical reconfigurable assembly way that is in performance. We're trying to make it comparable and more advanced compared to the DNA assembly. Yeah, if that helps you understand what's the difference between our approach and those DNA assemblies.
Yeah, thank you. That's interesting. So will it be more precise on the time scale, basically, and so you can assemble and disassemble really fast? Will it be, yeah, and is that um, is that something you want to achieve? And how about the different substrates, the solid substrates? Will it work on all kinds of different substrates, or will it vary a lot?
Yeah, thanks. For the substrate question, yeah, it is versatile for all kinds of substrate. As long as you have the CTC layer, you can coat the CTC on all substrates you want. Glass substrate, silicon substrate, and other substrates, anything. And so that is also very important of this technique. That is our platform is very comparable to the current silicon-based electronic technologies. It's so-called like CMOS technology. So which means our technology can be integrated with the currently popular silicon-based industrial technologies. And for the second question about 10 scale, yeah, that is what we are trying to achieve. But it is not that because it's hard to compare the time scale. Usually, I will see like for those assembly and changing structure experiments. For me, maybe it takes several minutes to assemble one structure. I'm not sure how about how like those DA assembly or other assembly skill, but I think yes, this time skill still can be improved. And also we are developing different kinds of ways to achieve the like faster and more efficient manipulation. The one way we can think about is we can using computer, some program to achieve the automatic control of different nanoparticles. And then we can also split laser beam, one laser beam split into several laser beams to do the parallel manipulation. So in that way, you can imagine we can use computer and to split different like several beams, and those like one beam can control each nanoparticle and they can move like together and assemble one structure, and then later it can be disassemble and then to assemble again. So yeah, we are working on like automatic control, parallel manipulation, those stuff to improve the manipulation efficiency.
Yeah, one last question, and then the cooling. So it will basically become immobile again, right? When it cools down, it will become immobile. Like, how long does that take, or is that pretty fast? And what's the temperature again that it has to heat up to become mobile, basically?
You mean for the laser cooling
Yeah.
experiments? Yeah, so laser cooling, laser cooling is a little bit different from those mobile, like those solid state experiments. They are they are done in liquid environment, and they are pretty fast. So I will see maybe in some microsecond, because it's something related to the heat transfer, and those heat transfer and temperature equilibrium actually reaches in a very fast time scale. Maybe I will say less than 1 millisecond, probably in something maybe microsecond or nanosecond. Yeah, it's pretty much fast.
Yeah, that's really interesting. Do you think one day you can put these in cells, like in neurons or in
Yeah,
different
yeah, yeah, yeah,
cells?
yeah, definitely. So I actually have I have some ideas in mind. So as you said, I would like to put those laser cooling nanoparticles inside cells or other like biological tissues, and then we can locally modulate the temperature of those tissue in the tissues and cells, and then we can locally modulate the temperature, and we can locally monitor those biological processes that are gonna be super interesting and will provide a lot of insights for metabolism and those biological like disease and cancer cell, those cell evolution, a lot of stuff. Yeah, I'm not I do not have much like biological background, but I do envision that this will bring like very like new possibilities to the life sciences and biomedical engineering. Yeah.
Yeah, I want to give other people. I could ask more about the cells, but I want to give other people opportunity to ask. So please go ahead, everyone. Flash your microphone and ask away. Thank you.
Yeah, it's really fascinating and captivates the imagination for the kinds of devices that can be just for some toy devices or maybe not so toy. Um, could you well, what rotational periods in time have you been able to achieve for the rotating the motor?
Yeah, that's a good question. So sorry I didn't put the image in here, but if you go to the SS Nano paper that we have a figure shows the rotation time. But briefly, I can talk about here is that it's at the current stage, it's kind of not that controllable, and it varies a lot for different kinds of nanoparticles. Actually, it's kind of a good thing. At least it means we can control the geometry of nanoparticles to control it, right? So what we can achieve is like the rotation rate, of, like, for example, from like 10 RPM. RPM means like 10
Hmm.
rounds per minute, from 10 to maybe up to 300 RPM. That is for 300 RPM, which means for like it's like 5 rounds per second. Yeah, it can go pretty fast, and sometimes it's slow. So it depends on the geometry of the nanoparticles we are targeting at. Yeah.
Right. So, size and it would as well as radius would
Yes.
affect
Yes.
the period. Is there? I mean, would it be advantageous to etch a track into the substrate and have it, in essence, roll around in the track for additional stability?
Um, yes. So if you have a track on the substrate, that will be, I think it will be beneficial, but then you kind of involve like additional steps to achieve the model. So at the at the at the current stage, we didn't consider adding those tracks, but probably in some specific applications, if we are really targeting some, for example, targeted delivery, cargo delivery on solid substrates, that we can build some tracks, then we can build those nanomodels as a shuttle, right? You can
Hmm.
transform one thing, like one cargo, from one side to the other side along the track. I think that is also doable. So just imagine like you have a car in the nano world that can drive you
Hmm.
and can transfer cargoes and stuff at nanoscale. So it was very interesting. Just you imagine you scale down the real world to the nano world. So you have the car, you have the bus stop, you have this a lot of stuff. So you can, like, our nano model can basically act as like nano car, can transfer things and along the track or without the track. Yeah, it's interesting if we imagine those things, and then we can like develop those like step by step. Yeah.
Well, I suppose also the just as a last question, the position of the gold nanoparticles, say, would affect the conductivity across the inner and outer portions, and if there was some patterning, um, you could in essence control and modulate the conductivity across different channels. It's just I mean, it's interesting to just let the imagination run wild.
Yeah, yeah.
But
Thank you. Thank you. Yeah.
fascinating. Thank you.
Yeah. Thank you.
So, forgive me if I didn't follow, but could you go over again all of the forces that are acting on the nanoparticle in the motor to cause the rotation that's observed?
Yeah, thank you. That's a great question. So I apologize for not going in too detail. So if we go to slide 23, yeah, because this is probably a little bit professional, or so it's a little bit abstract, actually, a little bit hard to understand. So I kind of like not going to very detailed in my presentation. So basically, I think, yeah, I should have put uh, the figure in the slides. So basically, in figure 2C, that's in the paper, it's not paper. Sorry, I didn't put it in here. But briefly, so in this nanomodel case, there are three forces will like playing a role in the rotation. And because of the nanoparticles is rotating in plane, right? So we ignore all the out of plane force. So in the in plane, we will have first the optical force, and the optical force is primarily in the radial direction, because it's also very understandable because the tangential direction, the optical force is small and can be negated. And the second is the thermocapillary force, and this thermocapillary force is because the nanoparticle has non-spherical shape, and the temperature distribution is non-uniform at the surface. And this will, for example, if the nanoparticle is spherical, and it will cancel out in every direction, and the net force is zero. But for the non-spherical particle, all the forces cannot be cancelled, and there will be one net force and net torque. And this net force, the direction of the net force will be dependent on the orientation and the geometry of the nanoparticle. So we can think about the thermocapillary force is the key here, but it can only be controlled by orientation of the nanoparticle. And the third force is when you have the nanoparticle moving around the laser, and when like when you have the quasi-liquid structure because of the phase transition of CTAC, there will be a drag resistant force. That force is like the resistance force, but it has to be there to balance with the driving force to achieve the um, stable rotation. So basically, if you see the right panel of the slide 23, the solid, the dashed green line shows the total force we calculated for some stable orientation in the radial direction. And then you will see I use another vertical dashed line to mark a point that is like the balance point where the radial direction is almost zero. And at this point, the particle will remain on the track because they kept the same laser particle distance, right? And at this vertical point, you will see the pink line. That is the total. Sorry, not the pink line. It's the green dashed line. Oh, sorry, the green solid line. That is showing that there are a total tangential force that is around 20 photonewton, and this is the driving force to to move the gold nanoparticle around the laser beam. And this driving force is also balanced with the drag resistant force. And it's kind of like the coupling between the optical force, thermocapillary force, and the resistant force together to achieve stable rotation. And when the particle is at a certain orientation, yeah.
And so does the total behavior result from the particle essentially spinning until the force becomes tangential, and then it takes off in the circle in the orbit?
Yes, that's a good question. So yes, that is actually how it is. At least at the current state, what we believe it is. So if you look at the slide 24, there are 3 videos. If you look at the second video, so if we put everything we calculated, so the particle will initially undergo a reorientation process. That is very fast. It takes less than millisecond, and it will, automatically go and orientation itself until it finds an equilibrium orientation. And after it reaching this orientation, the particle can stably rotate around the laser beam by the interplay of those all the forces.
Thanks.
Hi, yeah, Dr. Lee. This is thanks. This sharing this interesting work, and congratulations on the many interesting results that
Thank you.
given the very productive research. The following on Eli's question, I'm also curious of the similar the modeling part. So have you? Is it easy to repeat this experiment that at a various different conditions? For example, so given that your explanation that then say a very spherical particle that will, you will see no rotation, and so what kind of fields that you mentioned there's a transient stage that you need to have it to self align in a way that before the rotation. So is this a force that the net tangential driving force a also a function of the thermoplastic? I mean what do you call the surface?
Thermocapillary.
Yeah, that I mean the plastic beneath it, or and is it a function of the frequency as well? Say I'm shining a different spectrum of light, and is it like a dipole as well? Just
Yeah,
curious
yeah,
how
yeah.
well
That's
it's
that's
understood as
Yes, yes, that's a very great question. I can see you are also an expert in this optical, maybe photonic field. We can communicate more later. And but yes, that's a great question. So, those force calculation, like all of this stuff, yeah, we have to choose a specific wavelength. So if you recall the video I showed in slide, let me check, slide 15. That is the nature communication work. So basically in that work, we mentioned that we can tune the working wavelengths of those techniques in the opto-thermally gated photon energy technique. If we using green light for gold nanoparticles, like what we are using, we can move the like very smoothly move the gold nanoparticles. We are pushing it away, right? But in the nanomotor work, slide 22 and slide 23. So what we do is we using another light, 660 nanometer light. That is red light. So what we do is we have to using an off-resonant light. In that case, we are trying to reduce the optical scattering force, because if the scattering force is too strong, the particle will just be pushed away. So that's why in the slide 23, we are I'm concluding that um, we are manipulating all of the forces together to achieve the stable rotation. And you are right, it's dependent on laser wavelengths, focal numerical aperture, and the particle size, and a lot of stuff. And also I have to admit here, not all particles can be rotated at the current stage, because if you see the left image, it's like statistically the particle shape is random, right? So there are some particles can work, some particles are not work. And we have also mentioned that in our paper. And also another thing is like we cannot control the rotation direction. Some particles rotate in a clockwise way, some particles in a counterclockwise way. Yeah, but we believe that at the current stage, we are trying our best to explain the phenomenon by proposing the opto-thermocapillary force. And also we are also trying to work on design new nanoparticles with like design the shape to further prove our hypothesis, and also to improve and to achieve better control of the nanoparticle. Yeah.
yeah. So my signal wasn't very good. So yeah, I hear most of your answers. Yeah, interesting. So my impression is this is still have a great potential, to explore, right? So that's interesting. Yeah, I definitely contact you when I understood the work. So for the earlier technology that so of course, if we have time, we can, if you care and interested in explaining what's going on in between, in this the CT, AC, and the Golgi particle, how they. But my next question is for the thermal, the tweezer part. So is the and also the scattering driving part. So are you limited by the laser field available to you, or can you change that? For example, can you uh, adjust the angle of the light field?
Oh yeah, yeah, yeah. That's a great question. So yeah, we mentioned that yeah, potentially if you adjust angle, by because if you see the set 14 where like the laser is is normal instance, but if you do like oblique instance, like you using different incident angle, it will definitely improve the modulation frequency. But yeah, in my previous lab, we are limited by the facility. We cannot change the incident angle. But if we do that, I believe it will be like huge improvements to this manipulation frequency. Yeah, of course. And also in the tweezer part, it's also interesting if we like doing something like total internal reflection configuration that to shine the laser to the subject and without letting the laser go out of the like transmit from the subject. And in that case, we can further eliminate the effect of optical force and to reduce the photon damages. Yeah, I think that's a very good question and very good suggestions. And but unfortunately, it's limited by the facilities we have in our lab that before. But we will consider doing that later if we have the condition. Yeah.
Yeah, thank you for the answer. I'll let our you know yield the mic for now, and I'll ask you more later. Thank you.
Thank you.
Dr. Shah, did you have a question?
Yeah, thank you so much for sharing your work with us. I was a little bit late, and my question from you is about the possibility of somehow you just explain about the theory behind that, and I was just wondering of using that with the qubit gate for production of the qubit gate and saving the data and transferring the data. And I was just wondering, maybe you have further information. And then you just mentioned about the configuration assembly. And I was just wondering about the formation of the multiple quantum. And I was just wondering, do you have any further information about that or not?
Um, yeah, that's good question about like for the future work. So far, I will say, I think I briefly mentioned about like the future work on how to improve the manipulation, efficiency and throughput. I think our first step will be, to integrate those manipulation techniques with, computer controlled automatic control and parallel manipulation capability. And if that one has been achieved, and then later with those fast manipulation, we will be able to assemble different structures to use it for data storage and rewritable optical data storage devices. I mean that I think that is the later work after we achieve those automatic and parallel control. Because at the current stage, if we're using like manually control those to achieve those data storage, it'll be kind of impossible. So we can only do some achieve some very at the small scale tunable devices at the small scale. So but yeah, we are working toward that. So I think one of my colleague at UT Austin, he's currently working on the automatic control to making those opto-thermally gated photoenergy programmable. And next, I think we believe we are going to work on those optical communication field and trying to develop those reliable optical data storage and devices like that.
So by considering the optimal, control theory that you just mentioned about the mechanical geometry, do you see any relationship between the mechanical geometry and, for example, a superposition state that we can just get an idea about?
You mean the nanomotors?
Yes, it can be that one, and it can be in the form of the reassembling.
Sorry, can you repeat the question? You mean the
Yeah,
relationship between the geometry and the...
you just mentioned about the mechanical geometry that might be the next step that you want to take. And I was just wondering, do you think that is there any relationship between this mechanical geometry and finding the, for example, superposition state that we are using for the data information, and it just support the theory behind your research?
Yeah, actually, I'm not probably I'm not sure if I understand correctly about the mechanical geometry you mentioned. But I believe, we are working on, developing active nanostructures and active, metal surfaces or structured materials based on the technique, and assemble the nanostructures into different configuration, and using that to disassemble and reconfigure it into another configuration. So we are working on that, and we are definitely exploring the material structure and function relationship, and toward different on-chip devices. Yeah, I'm not sure if this answers your question.
Thank you. It might be the next step. So thank you so much for answers.
Yeah, thank you for the questions.
Guta, Aya, and Nina, do you have a question? Oh,
I just wanted to thank you for your time, Doctor, and because it's the first time I've had exposure to this level of detail for nanoparticles and nanomotors, so I feel like I've got a lot of information to process, and I haven't done that enough to formulate the questions, but I'm thankful for the knowledge you've shared this evening. Thank you.
Thank you.
yeah, thank you so much. Frank, you had some more questions. Please feel free to ask.
Sure. So maybe my there's something that unclear regarding the CTAC in so in your modeling. I'm curious how have you so in detail. So this you as I understand right now there's a tweezer. I mean the laser the high in what do you call very intense focal point. Then there is very curiously there is a very certain or stable equilibrium distance of your orbit r, right? So and there's also that the gold particle is absorbing heat because from your cartoon like you share there's a red kind of a thermal melt energy that melts the CTAC beneath, and so these are all contributing so the gold particle is melting the ice, say as it goes, right? So it is quite complicated to me, I mean, at this stage. I was just wondering, so my question essentially is the role of uh, the surface polymer that plays in this in the thermocapillary force. Yeah, how is it a very already well established in the field, this thermocapillary force field?
Yeah, that's a great question. So, yeah, the first role I believe here, as what we believe, demonstrated before, the for the manipulation assembly, it definitely help modify the particle substrate interactions through a reversible phase transition from solid phase to a quasi-liquid phase. That is the first thing we are very sure about. And the second about like the role of CTAC, and that I believe here we're talking about the quasi-liquid CTAC on the opto-thermocapillary force. So I think it is well established theory to describe the opto-thermocapillary force. So basically, if you have those non-uniform temperature gradient um, at a interface, like liquid solid interface or liquid liquid interface, you can use some equations and integrations to calculate the optothermal the thermocapillary stress, and then calculate the thermocapillary force. I believe it is well established. So here what we do is we treat the quasi-liquid CTC as a liquid, and we do have use some measurement to calculate the not calculate, actually we use experiments to measure the surface tension of the quasi-liquid state of CTC, and then we use that surface tension value here to calculate the thermocapillary force. So we believe the thermocapillary force part is should be well established and should be very reasonable in this case. But there may be some other stuff we didn't consider about. Maybe they also played a role. But at the current stage, we're doing the best to understand. And so far, the theory we proposed is very consistent to all the experiments we observed.
Right. Oh, go ahead, Serena.
Oh, okay. I was, imagination still running. So on the gold nanoparticles, have you thought about, or do you have any plans on looking at, functional derivatives in the sense of, okay, say you take a sulfide with a carbon tail on it. Those like to coat the gold nanoparticles, but you can put, say cross-linking groups in the sense where you can manipulate those particles to come into close proximity. You can arrange them close and hit them with UV and cross-link them and develop these more complex shapes and patterns. But even in the controlling or investigating the shape of the particle assemblies in that sense, for their different effects in the nanomotor context. Um, I'm just curious how it might be an approach to have more control over the specific shape by building up, um, tight assemblies or coupled assemblies of the nanoparticles. But even, what would the effect of surface functionalization have on their properties? I don't know if you,
Yeah, it's a very interesting, and to like involve polymers, cross-linked materials like those stuff, and also surface treatment of gold nanoparticles and other nanoparticles. It will definitely be very interesting to dig into. But in another way, it will actually involve more complexity in the system. So at this stage, we're probably not going to do that before. Before we really understand what's going on, and we really, like, for example, as I mentioned, I think our first step is here. We want to first understand the role of geometry first, and we want to show that we can when we show that we can precisely tune and rationally design the geometry, and then later I think it will be very interesting to, of course, to add surface functionalization and other polymer materials as the environment stuff to make the system more versatile and powerful.
yeah. Did you say earlier in the talk that when you got the particles close enough, they dimerized? Um,
Mm-hmm.
was the dimerization? Did you characterize that in more detail? Do they actually fuse, or what's going on there?
Yeah, so that happens in the slide 18. So that is when we do in the opto-thermocapillary photoenergy. So we are energy one particle to another particle, and when they are close enough, they become a dimer. So, but if you take the SEM images, there are still two separate particles. They are just very close, and so there will be near field coupling between those nanoparticles. So if we measure the scattering spectra, as we show in the left, bottom left, you will see the one peak of the scattering spectra actually split into one peaks. That is because there are like two near field coupling mode. Um, the warm surface plasma resonance like split into two plasma resonance mode. Yeah.
I see. Thank you.
Thank you.
Oh, hi, Jingang. So if I may, I would like to pursue a little bit more. So see your slides of the showing the model is quite why I'm so amazed, because it's definitely reminds me of magnetic kind of rotation, right? So is it so you mentioned some there's factors possibly that you have not included. Is the magnetic field or distributions within the particles, have you dealt with it and conclude that it's not important?
Yeah. Okay. So I think Currently, it is well accepted that for those plasmonic nanoparticles, the magnetic field it should be very negligible. But if we're talking about dielectric nanoparticles like silicon nanoparticles, probably there will be a magnetic force, magnetic field. But for the gold nanoparticles, I kind of believe the magnetic field is not as important as we um, like discuss right now. Yeah.
So does the particle spins, as it doing the orbital rotation? Have
We
you?
we don't know, unfortunately. So as you can see from the images, like the videos I showed, so we are still relying on optical imaging of those nanoparticle. But yeah, later, so we have something in mind like to integrate this laser system with TEM, like transition electron microscope. So if we can do that in situ TEM, and we can probably see much more clear on what's going on, like all the process like the CTSA phase transition and the particle orientation and particle rotation, all the stuff. But that is future step when we have. But the facility is not easy to get. Integrated laser with TM and those stuff. But one day, if we can have that facility, probably it will be a good platform for us to further study very thoroughly about those process.
I see. This is actually very intriguing phenomena. Yeah. I mean, there's definitely stability, right? Although you mentioned that it varies, is somehow there's you probably can figure out some empirical rule of thumb what type of shape, although not spherical, but do have some symmetries, right? So maybe, I mean, say a very irregular ones also doesn't. Maybe I don't know if you have collect those data, but yeah, this is definitely intriguing. Also, you mentioned the direction of the rotation is uncontrollable yet. Yeah.
Yes, I think in the future, those, as you imagine, so it probably we can figure out some like rules and to get those solid state models, and also for the direction, maybe we can also involve using some like herald source or other like to design the geometry to achieve to control the rotation direction. I think that's it. Yeah, they are all possible. Yeah, in the future with some extended work.
So, given the time available, I will ask Karina. I'll just have a quick last. I mean, for now, last question regarding the solid states. The optical tweezer, optical electronic tweezers. I'm quite interested in that. In your research, in your sharings, you mentioned comparison between your work and the plasmonic tweezer, which is superior. I mean, yours is better. How do your tweezing tweezer compare to the optoelectronics tweezers?
So you are just for the opto-refrigerated tweezers. I think the most most notable advantage here is the non-invasive manipulation. So as we mentioned, like for all of these other techniques before, if when you have light, when you have like nanoparticles, other stuff, normally they heat up, but now we have those laser cooling capability that to trap, and especially for simultaneous nanoparticles and materials to trap them uh, at the cold spot and without causing thermal damages to them. I think that is the biggest advantage for our technique compared to other techniques.
I see. Thank you, Karina.
Yeah, thank you so much. Do we've been going for 2 hours, so probably getting tired of speaking with us. There was a question in the chat, if that's okay.
Oh
If
yeah, sure.
the nanoparticles would be toxic if we would use them in cells, but I guess that's hard to answer right now.
Uh, yeah. It's a. I will say. Yeah. As I'm not a biologist, but I will see good nanoparticles actually definitely not toxic, because there are tons of research using good nanoparticles for drug delivery or like cancer therapy, opto-thermotherapy, a lot of things. I will see those nanoparticles should not be toxic. That's what I've based on my understanding and knowledge. Yeah.
Yeah, thank you. And yeah, I would have more question about using them in cells in the future, but I think we would need to invite you back for that once you maybe are starting to look into using these for cells and also thinking about but the real advantage you have here is that you can like the really cool thing I think is that you can move particles on a solid substrate. How much can it move, like compared to let's say you have like how many nano particles could you move and how many would you need? Like, can they move more than their own weight, basically, less? Like, what's the percentage of what they can move?
Yeah, so for that if you look at the slide 15, so for those optothermally gated photoenergy, the answer is like I think almost 100%. You can move all of those particles, and and also the CTC itself it can be replaced with other materials. So I will say it almost 100%. So I think because I think for this work, I think the principle is very clear, and we are using, opto, the phase transition to help reduce the friction force, and we're using opto scattering force to push nanoparticles. I think that this work is pretty much 100% workable for all nanoparticles, and as Frank he envisioned, if we have the laser, the incident angle is not vertical, so if we tune the incident angle, we can further increase the scattering force to improve the modulation efficiency. So I will see for this part it should not be a problem for it should be like general to a lot of I think all kinds of nanoparticles and materials. Yeah. And also, as I think, as a quick summary of all the research, you can go to the last slide, 26, and also like pretty much what I want to say is that all the research here, what I do is an extension of optical tweezers. So optical tweezers is powerful, and I hope my research can make the optical modulation techniques more powerful by using, the first is to achieve non-invasive manipulation, and I will envision later, and I think maybe personally I will work on the using these techniques for more biological studies to reveal more biological insights for the development of life sciences. And the second is all about to extend the working environment. That is like something perhaps cannot be achieved, and I will envision it can be integrated for more, to study the physics and to study the optical coupling between those nanostructures, and also to integrate those platform with on-chip devices and MEMS or NANS or robotics and other stuffs. Yeah, I think that's the conclusion and take-home messages that I want to convey in this presentation.
Yes, thank you so much. It will be very exciting to follow your future research. It will be for sure very promising, and thank you for giving this wonderful presentation, answering a lot of our questions, and yeah, we wish you all the best for your future, and thank you for coming and taking the time to explain all of this to us. We appreciate it.
Thank you. Yeah.
Okay, we're closing the room. Before we do that, if you like presentation and discussions like this, follow the club. We have tomorrow Dr. Lafay talking about thymocyte cell type discovery and leukemia, cancer research. That's really interesting and will open up a lot of hopefully specific treatments. And then we will have Dr. Kolahama and who will be talking about using AI to diagnose dementia more accurately. And on Thursday, Dr. Dmitry Kirev, he will talk about an ETA2 for continuous blood pressure monitoring, which is really important, especially to monitor it at night for people that have issues. So, yeah, will be another interesting week. And thank you, Yang, for starting this week with this amazing talk. We really appreciate it. And thanks for all your hard work and for this presentation.
Yeah, thanks for the invitation and thanks for all the interest. Yeah.
Okay, we'll close the room in 3, 2, 1. Bye,
Thank
everyone.
you. Yeah, thank
Thanks,
you.
everyone.
Thank you.
Thank you. Bye.